Rightio, so we're on now 10B and 10C. You can follow along in the OneNote. Make sure we're on the right page there. A quick summary of the terms with which you're already familiar, so this won't take us very long. A sample space, they like to use epsilon for the sample space. That's okay. You too, on your birthday especially, that's nice. For a random experiment is a set of all possible outcomes. So the sample space list of all possible outcomes, we should remember that when we roll the die, the sample space, 1, 2, 3, 4, 5, or 6. We've done that a million times. An event is a subset of the sample space. The probability of an event A occurring is denoted by PR bracket A. We've seen that before. Some books have PR, some just have P. I tend to use PR just to make it clear, but up to you. The rules of probability for finite sample spaces. The probability of an event is greater than or equal to 0. We can't have negative probabilities, can we? Would there be an upper limit on that probability? I would think so. 1, yeah, they didn't talk about that, did they? They should have said that as well. Probability of any outcome must be less than or equal to 1. And the sum of all the possible outcomes, the probabilities of all the possible outcomes is equal to 1. We knew about that. If all members of the sample space have the same probability, then the probability of each one would be 1 divided by however many things there are in the sample space. So if we think about rolling a die again, just a regular 6-sided die, the probability of getting a 1 is the same as the probability of getting a 2, same as the probability of getting a 3, 4, 5, or 6. There are 6 options. So each one has a probability of 1/6. Sometimes things have equally likely probabilities. Sometimes the probabilities are different. It's not as if we haven't seen that before. The basic rule of probability, the probability of an event is the number of ways that event can occur. The number of outcomes in set A is the way they're describing it there, divided by the total number of possible outcomes. None of this is new to any of you. Finally, complementary events, complementary with an E. Complement of an event. So if we have an event A, the complement we write as A dash or A prime. And that's just 1 minus the probability of A. It's everything that's not included in A. We were looking at that with our set notation yesterday. So again, nothing too surprising. In some instances, we cannot calculate a theoretical probability because we're interested in things which can't be analysed in that way. So if it's a roulette wheel or rolling a die or tossing a coin, yep, we can use theoretical probability. If it's what's the likelihood that the next person through the drive-through at McDonald's orders a hash brown? Well, that's not a probability event that we can use theoretical probability for, but what we could do is use past history. So our knowledge of all of the different customers who've been through that drive-through before, we could find the relative frequency, how many of those people had ordered a hash brown, and we could use that to estimate the likelihood that the next person would order a hash brown or whatever else it was that you were interested in. So that can be the number of times a particular event occurred divided by the number of previous trials that have occurred. It could be if you're planning to have a bake sale and you want to know how many drinks to order and how many of each type of drink to order. We might know from our last bake sale, oh, we ended up with a whole bunch of Sunkist left over because let's face it, no one really likes the orange drinks. Everyone wanted the Pepsi Max. It sold out in seconds. So we've got to make sure we order more of those this time. The rules of probability always hold the same. Okay, let's move on to something, not a super basic one, slight step up. In grade 9, this would have been thought of a little bit tricky, but you guys are going to be fine. A random experiment may result in outcomes A, B, C, D, or E, where A, B, C, D, and are equally likely, and E is twice as likely as A. So they're not all equally likely. They want us to then go ahead and find out the probability of E. Although I am confident you can all do this in your head, let's think about how I would set it out to try and show it nicely. So I'm going to say let the probability of event A equal X. I don't know what it is, so I'm going to use X, very creative that way. Therefore, I also know the probability of B is the same as the probability of C, is the same as the probability of D. They are also equal to X because they were equally likely, weren't they? Boom, yeah, all over it. But you've got to communicate this in an exam, so I'm trying to help you show that communication. You can do it all up here. You've got to actually get it down on paper. Probability of E, oh, look at that, I changed from having PR to just P. That was really sick of me. I'll go back to PR. The probability of event E, we are told, is 2 times the probability of event A. So it's therefore 2x. What do we know about the sum of all of our probabilities? It's equal to 1. X plus X plus X plus X plus 2X has to equal 1. 6X equals 1. X equals 1/6. So my probability of event E, which is the one they were asking about, that was equal to 2x, which is 2 times 1/6, which is indeed 1/3. Is that okay? There's a tiny bit of thought involved, but it's not particularly taxing on our brains. But setting it out, being able to communicate it is going to be important so that you get rewarded with those marks in the exam. So even though it's kind of a little bit frustrating when you can do something in your head to have to set it out, make sure you do anyway. The probability of the complement of B, the probability of B prime. Whenever you're asked for the probability of something not getting something, it's usually easiest to go 1 minus the probability that I actually did get event B. What was the probability of event B? 1/6. So therefore, the probability of the complement of B, not getting B, is 5 out of 6. Is that okay? I'm assuming it is. I'm seeing some nods. That's making me happy. All right, example 11. So this will be 10C already. 10B is really basic stuff you can do. 10C is now just using that past history, the relative frequency to estimate probabilities. You're going to be fine with this too. In order to investigate the probability that a drawing pin lands point up, assuming it's been thrown or dropped or something, Katya decides to toss it 50 times and count the number of favourable outcomes. Favourable this time is landing point up. She must be nasty. I would have thought that was unfavourable. And she found that it landed point up 33 times out of the 50. Mickey repeated the experiment and she tossed the same drawing pin 100 times and found that it landed point up 62 times. What is Katya's estimate of the probability of the drawing pin landing point up? So our estimate of the probability that it lands point up, is going to be the number of times it landed point up, which was 33, divided by the number of times she actually tried to do that, which was 50. What about Mickey? What's her estimate going to be? 62, yep, so probability point up. And I might put a little M after that and I put a little K after this one so we can distinguish between the two, is going to be 62 out of 100. And you'd work down the page, but I'm just getting it into here. 31 out of 50. We still simplify our fractions if we can. Which of these is the preferred estimate of the probability from these experiments? Have a think for 30 seconds and then tell your answer to the person next to you and see if you agree. Have a think first. I should now be humming some delightful thinking music for those of you watching this video, but you miss out. Maybe another time. I'm hearing talking, which means we've all made a decision, I think. Whose estimate is a better estimate, Katya's or Mickey's? Why Mickey? She's so fine. She's so fine. She's got hey, Mickey. Oh, someone's into it. That's good. Yeah, why? Why is it better? More trials. So usually with these probability, when you're using relative frequency, the greater the number of trials, the better the estimate. That makes sense, right? So that's very good. So we're going to say Mickey's because there are more trials. Part D, based on the information available, what would be the preferred estimate of the probability? What could we do to get an even better estimate than using just Cutchers or just Mickey's? Yeah, add them. My goodness, on fire. So the preferred estimate is going to be 33 plus 62 out of 150. What's that? 95 out of 150, which is going to be what, 19 over 30? Did I add up correctly? Good, we all agree? And we're done. Nothing too complicated about that. Lucky Last, I'll stop talking and give you a chance to do this one yourself first because you need to do some maths on your own. We have 4 minutes left. I'll give you 2.5 and then I'll just clarify. All right, so coming back and just checking if we agreed with each other on those ones. 183 out of 200. The book, when they do the example, likes to give it as a percentage or a decimal. I would always use fractions if possible. I think that's easier and you're not rounding off. I'm not sure why they're rounding off and introducing error into their answers. When we're combining for part B there, we had 183 out of 200 and then 87% of 300. So you just calculate that, add them together, 444 out of 500. You can divide each of those by 411 out of 125. If it asks for a percentage, give a percentage. If it doesn't, please just give a number between 0 and 1, preferably as a fraction. That's it. You've still got a minute left to think something mathematical before you run away. But that's it for the lesson today.